Okay, so in addition to the periodic trends that we just talked about, ionization energy, electron affinity, and electronegativity, there are some other key points that I want you to remember about the periodic table, because they're part of how we explain what we observe experimentally. Okay, it's somewhat arbitrary, but I think these are three major ones that I'd like you to keep in mind. So the first one is, let's call it A, is the so-called diagonal relationship. And then, so this is just something that you want to keep in mind. Is just that as in your second row elements. So here, we have lithium, we have beryllium, we have, then we go across boron, carbon, et cetera, et cetera. What you notice is if you look at tables of electronegativity and size, et cetera, what we'll see is that lithium and magnesium both have really similar electronegativities and size. And then this is the so-called diagonal relationship in the sense that they can, in some cases, substitute for each other and have very similar properties and reactivity. Sorry, that was a terrible diagonal. And then as we go across, you have aluminum, silicon, et cetera. What's past silicon? Nitrogen, phosphorus. So again, we have that same diagonal relationship. We have beryllium to silicon, beryllium 2+, aluminum 3+, boron, beryllium, aluminum, boron, silicon, et cetera. And so that's the so-called diagonal relationship, that they're very similar. And that's all you have to know, that they can occasionally substitute for each other. Okay, what's over here? Sodium. Okay, we just ignore that. That's not part of it. Okay. Very good. Part 2, okay, that was the easiest one. The more complicated one that I do want to talk about is the so-called uniqueness principle. You don't need to remember the name. But the basic take-home message of the uniqueness principle is that the second period elements, so this lithium, beryllium, boron, carbon, nitrogen, oxygen, blah, 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 they are very different in reactivity and properties compared to their analogs in the third row, fourth row, fifth row. So you might have learned that each group has similar properties, and that's generally true. So let's say silicon is very similar to below, tin, lead, et cetera. But the second row behaves very differently due to numbers that we'll talk about compared to the lower. Okay. So the major reason is that it's so small. So this is because they're smaller. And then, so the reason they're smaller is, again, we're in the second shell, but more importantly, if we think about the 2p elements, we're filling 2p orbitals, like that. But they don't have 1p orbitals, so there's no p orbital directly. There's no filled p orbital directly underneath it, so it's not as shielded. So it's going to be smaller. And then, so this was the effect that we saw with electron affinity, in that there's that kind of discontinuity between the second and the third rows because of that small size. We can't push that extra electron in. Okay, and then again, this is the second factor that makes it really different, is that there are no d orbitals available. So they're the 3 d orbitals for the rows below, and then so because that makes them available for bonding and other properties potentially, and then so the fact that the 2p there are no 2d orbitals, then they're not accessible, and then so that also impacts their properties versus the rows below. Okay, so let's talk about kind of general effects of this uniqueness principle. So let me quickly erase. So we're still talking about part B, uniqueness principle. expect one, your kind of general takeaway that you should remember about the second row is we have high covalency, strong sigma bonds. And this has to do with, again, the small size, and then there's going to be high orbital overlap. Again, the key point, I think I mentioned from the last lecture, is that a key point about bonding and stability is the greater orbital overlap you have, the better, more covalent bonding you will have, because you have to share those electrons, you have to form molecular orbitals that are highly overlapping, for example. And then so if you want to think about, let's see, carbon-carbon versus silicon-silicon, we have our two p orbitals. And again, we're forming our two p orbitals. This is our sigma bond that we're forming. So they're pointed right at each other. They're overlapping quite well. In silicon-silicon, we're going to be further apart. Let's say like that. I'm kind of overdrawing it. And then so while the 3p orbitals that silicon has are indeed bigger, they're what's called more diffuse. Right? So the amount of kind of overlapping space that they're going to have between these two atoms is going to be smaller than in carbon-carbon. And so overall, that sigma bond is going to be weaker. So I have over here a table of these homonuclear single bond energies. Sorry for all the race of silicon. Oops. So here are strong sigma bonds. And so what you see here is generally, as you go down a group, so we're comparing lithium, lithium, sodium, sodium, the energies go down as we go down the group. So that's, again, because we're getting bigger, our orbitals are overlapping less well. And then generally, as you go across the period, they do get somewhat stronger. But there are some exceptions. So I do want to point out some exceptions here, which is that, so we're going across, we're getting stronger bonding. But then as we get to nitrogen, nitrogen, oxygen, oxygen, and fluorine, fluorine, you can see that these single bond energies are actually a lot smaller, and we no longer have like that it's higher than below, the PP, SS, et cetera, et cetera. And the reason for this is, so watch the exceptions. NN, OO, FF. And the reason for this is because if you think about, like, let's say an alkane, our CC bond, that's all well and good. If we think about the analogous nitrogen molecule, some sort of hydrazine, R2, 2, now we have lone pairs. So in this case, these lone pairs are actually, we have electron-electron repulsion between the lone pairs. So this is lone pair repulsion. And the same factors occur, excuse me, for oxygen-oxygen, fluorine-fluorine. They have even more lone pairs. So because of that, these single bonds are weaker due to the ones with lone pairs. So that's kind of like the exception of our uniqueness principle strong bonding. OK, and then the second part, which is directly correlated to the strong sigma bonds, is also, because these are small, we have good overlap of perpendicular pi orbitals. So we can have extensive pi bonding, the second row elements, that is. So again, our elements are close together. Let's say we have CC bonds. Again, so they're less overlapped than a sigma bond, so that's why they're weaker. But their atoms are close together. We can have good overlap over here. In comparison, silicon-silicon, they're further apart. They're kind of facing up. They're not pointed even at each other. So that overlap is very poor. And then so silicon-silicon would be like weak to negligible pi bonding. So let me move on. Oop. So here's kind of a table of more values. We're comparing, the left number is going to be the sigma bond, which for nitrogen, nitrogen is weak, again, because of that lone pair repulsion. But you can see this pi bonding is actually quite strong. So CC pi bonding also quite strong. But then as we go down the group, again, because larger size, further apart, worse overlap, our pi bonding gets very, very weak as well. So the pp pi bond is much, much weaker than the nitrogen-nitrogen pi bond. And that's the case also for heteroatomic pi bonding as well. So we have strong CO bonds, but weak silicon-oxygen pi bonding. OK, great. So those are two factors, pi bonding, strong high covalency. And then so another result of the uniqueness principle is that due to the lack of p orbitals and also the small size, you're always going to typically obey the octet rule. And also max coordination number of 4. There are some exceptions to this, but you often cannot access hypervalent carbon, for example. It's very, very rare. And in contrast, silicon that's 6 coordinate is very, very common. And so you can attribute that to also size, but also the possibility of d orbitals in bonding, which is what we'll use for this class. There's some more complicated explanations also that we won't go into. All right, and then the last thing is lower reactivity compared to the corresponding further down the group elements. So for example, CH bond doesn't oxidize in air typically unless you apply a lot of activation energy to burn things. And in contrast, a silane, okay, let's just do ours. Many silanes oxidize in air spontaneously, so it's more reactive. Okay, right. And then the last thing I want to talk about, sorry, these videos are getting a little long. So that was uniqueness principle. We talked about diagonal effect. This last one I want to mention is the inert pair effect. Part C. Okay, and then so the manifestation of this so-called inert pair effect is that in p elements, p group or p elements, elements with 5s and 6s electrons are more stable than expected. Okay. So what this means is that what we'll see is that as you go down the groups, so let's talk about, for example, okay, we have in the third row we have phosphorus, silicon. I won't go. I'll just use these groups as an example. Phosphorus has a very typical oxidation state of 3+. Trivalent phosphorus. Silicon is 4+. Right, we're in the fourth group. But as we go down, we have tin, then we have indium, then we have thallium, and then we have lead. And of course, there's other ones as well. Let's say over here is bismuth. So our common oxidation states for indium has both 1+ and 3+ available. Tin also has 2+ and 4+ available. So if you think about it, in the the silicon 4+ oxidation state, we've removed both p electrons, and then we've also removed the 2s electrons. So then we're down to, this is your kind of like noble gas configuration in this 4+ ion state. In tin 2+ and indium 2+, we still have that s2 configuration. We've removed only the p electrons. And then, so because of that, oh no, I messed it up. What have I done? No, that's right. Sorry. Just had a brain fart for a second. So that's the so-called it's more stable than expected. We didn't remove it when we formed the compounds. And then lastly, if we go even further down the group, thallium's most common oxidation state is +1. You can see +3, but thallium 1+ is more common. And then lead 2+ is more common than lead 4+. Bismuth 3+ is more common than bismuth 5+. Oh, I know what I messed up. Haha, sorry for the problem. This is aluminum. That's why. There's something terribly wrong. I couldn't figure out what it was. I apologize for the error, but I'm also too lazy to go edit the video. So this is aluminum 3+. Thank you. Phosphorus was over here. All right. So, OK, where was I? Yes. So again, these configurations, we still have our s electrons. So that's what the 5s and 6s electrons, more stable than expected. And so the reason for this is, OK, so reasons. One, here we're down in these like lower groups. We have filled d electrons and f electrons, or d orbitals and f orbitals nearby. So again, the d f orbitals are bad at shielding. So these 5s and 6s electrons see a quite high Z effective. OK. And then because of that, they're more tightly bound to the nucleus. You can't excite them out as readily. The second reason is, as you get, we just talked about it, but larger elements have weaker bonding. And that's because the orbital overlap, the orbitals are more diffuse. The overlap is worse. So when you think about forming a bond between, let's say, thallium and chlorine, we want to get those electrons out to kind of share with the chlorine. And then so these 5s and 6s electrons, they're kind of, they're held very tightly into the nucleus because of this high Z effective. So the energy price you want to pay to form that bond and get that electron away is not sufficient because of the weaker bonding. So it's kind of like the play of these two factors, like how much energy are you going to give me for the bond to take this electron away from my core. So because of this price isn't high enough, because of weak bonding, we can't get these electrons out. So then we see this inert pair effect. So often you can have just like this thallium, lead, or bismuth with just like the lone pair kind of sitting on itself rather than participating in bonding. OK, so that's an inert pair effect. Some people find it very confusing, so let me know if you have any questions about this. But this is the ultimate manifestation. You'll see these higher oxidation, or lower oxidation states rather, compared to the elements above it.